Hello and welcome back to PC Retro Programmer. In the previous video we started to look at the possibility of a 320 by 200 16 color linearly addressed graphics mode on the Tandy 1000SX. And what we've managed to convince it to do so far is to use a single bank of 32 kilobytes instead of the usual 4 banks of 8 kilobytes. But now that it doesn't find the other 3 banks, it repeats the same scanline 4 times, taking the information always from the same bank. Now, in order to stop it doing this, we need to convince it that there's only one bank, and the way to do that is to set the number of scanlines per character to 1. So in order to accomplish this, we have to fiddle with the CRT controller registers. Now you might recall that the Tandy 1000 doesn't have an MC6845 chip, and it only emulates this, but this does mean that all of those CRT controller registers that were available on CGA are still available and work the same way essentially on the Tandy 1000SX. So the first thing I'm going to do today is discuss the values that are used in those registers for the ordinary Tandy Mode 9, and then I'll talk about the changes that we're going to need to make to get our linearly addressed mode to work. And of course this is where we could start to run into troubles. It's not at all clear that the MC6845 emulation of the Tandy 1000SX is going to accept the values that we need for our linearly addressed mode. Now at first guess you might imagine that these CRTC register values are going to be the same in Tandy Mode 9 and CGA Mode 4. After all, they're both 320 by 200 color graphics modes. But as you can see, the values are really quite different in these two modes, both in the horizontal and the vertical directions. And it's for subtle reasons that I want to explain right now. So in the vertical direction, it really boils down to the fact that there are 4 banks now instead of 2, and I'll explain how that affects the values shortly. But in the horizontal direction, it's not obvious at all why the values should be different. After all, you've got 320 pixels across in both of these two modes. And it really boils down to the fact that the original 6845 CRT controller chip on the CGA card thinks of the world in terms of characters, not pixels. It's a character device. And the CGA card really just co-opts it for producing a graphics mode. In fact, if you look at the values that are used in the 40-column text mode in CGA, exactly the same values are used for the horizontal parameters as in the 320 by 200 4-color graphics mode. First of all, the CRT controller is told to expect 57 characters across the screen in total. This is 56 plus 1, it's always this value plus 1. And this includes the horizontal overscan region. Of this 57, 40 are in the active region where the characters are actually being displayed. Now, the other 2 values are to do with the horizontal sync pulse. This is a pulse that the monitor needs to know when it has to retrace to the left-hand side of the screen. And this happens after 45 characters in the horizontal direction. And for whatever reason, this pulse is 10 characters wide. Now, the way the CRTC works is that it outputs an address called the Crtc Address that can be used to look up in video RAM which character should be being displayed at the current location. So this Crtc address is being updated whenever we're in the active region. So on the first character row it would be updated from 0 right across to 39. On the next character row it would be updated from 40 to 79. On the next character row from 80 to 119 and so on. Now in the CGA 40-column mode, it's not quite so simple as just using this Crtc address to look up video RAM. And that's because you actually need 2 bytes for each character in a color CGA mode. You need 1 byte for an attribute that contains the background and foreground colors, and another byte for the character, that's the ASCII code of the character. And so it's actually 2 bytes per character, and so that address gets multiplied by 2 in the case of the CGA text modes. Now it's important to understand that the values that are in video RAM in a text mode are the attribute and character bytes, and not the pixel information. So in a text mode, the character byte, the ASCII code, is used to index into character ROM to get the pixel information for that character. In a graphics mode, it's quite different. The pixel information is directly in video RAM. So the CGA card co-opts this character mechanism and this updating Crtc address in order to produce a graphics mode, and it uses the Crtc address to index directly into video RAM to get the pixel information. And so basically across the first row it's going to get addresses 0 through 39, and across the second row 40 through 79 and so on. And so it just uses those addresses to look up the pixel information. But it still uses a multiplication by 2. So this means that every time this address gets updated that the Crtc is outputting, it's actually moving 2 bytes in video RAM. And because we can fit 4 pixels per byte in video RAM, each pixel is only 2 bits wide, this means that we get a total of 8 pixels per character in video RAM. And so if you have 40 characters wide, then 8 times 40 is 320 pixels. So that's how we get our video information for the graphics mode on CGA. We just look it up directly in video RAM just by multiplying the Crtc address by 2. It's a little bit more complicated than that, and I'll explain why when we deal with the vertical section. But for now, let's think about Tandy Mode 9. Here we have 16 colors instead of 4, so each pixel is 4 bits wide instead of 2, which means that we only get 2 pixels per byte instead of 4. And so that means that with 40 characters of 2 bytes each, we would only get a resolution of 160 in the horizontal direction. So we need to up the number of characters to 80 if we want to have 320 pixels across the screen, just because of the fact that each pixel is now taking twice as many bits as we had in the CGA mode. So that explains why these values are basically twice the values that we used in the CGA mode. This value is also twice this. Remember, you have to add 1 to these values, so this would be 114 and 57. Now, the horizontal sync pulse width is not quite twice, but it turns out that in CGA you don't really need to use a width of 10. You can actually use a smaller value, and presumably the Tandy people just decided to pick the smallest value they could actually get away with comfortably on their hardware. Now in the vertical direction, I'm also going to explain how the 40x25 text mode works before going on to the graphics mode. And by the way, the graphics mode actually uses different values here than the text mode. In the CGA 40x25 text mode, the Crtc is told that there are 32 character rows in total in the vertical direction. It's always this value plus 1, but that's actually not everything in the vertical direction. In CGA, we're going to have characters of height 8 scan lines, and so 8 times 32 would only be 256 scan lines, and that's not enough for the CGA monitor, which is based on NTSC. It needs 262 scan lines, so we have an additional 6 to make up, and that's the value that we put in the vertical adjust register. It can just hold a small value, basically the difference. And the 25 is for the active region. It's a 40x25 text mode after all, And so this is the number of character rows that actually have characters that are displayed. The rest is the vertical overscan period. Now the vertical sync position is a little bit higher than this value. It's between these two essentially. And if you move that about, what's going to happen is the vertical retrace of the monitor is going to happen either earlier or later in that vertical overscan period. And so that'll have the effect of moving the screen up and down effectively if you fiddle with this value. And the same will happen if you fiddle with this value. It'll just move it in the horizontal direction instead. Now, when displaying characters on the screen, it turns out that the Crtc address that we talked about earlier, that's not going to be sufficient. We use that for looking up where in video memory the character byte is, and the character byte told us what character was going to be displayed, but it tells us nothing about which scan line of the character is being displayed. So for that purpose, the Crtc outputs another address called the row address. Now this is very badly named. It has nothing to do with the character row on the screen. The row address is only called that because that's what the pins on the chip are called. The row address is the scan line within the character. So for 8 scan lines per character, as we have with CGA, that row address goes from 0 to 7. That 7, by the way, is this value here. This is the maximum scan line within the character, and the numbering starts at 0. But this is going to cause a little bit of a problem for us in the graphics modes, because it means that the Crtc addresses have got to be repeated 8 times, basically for each scan line in the character row. And so that's not what we want in a graphics mode. We're not outputting the same thing on each scan line of a character in a graphics mode. If we did that, we'd just end up with repeated scan lines. Because remember, all we're doing is taking that Crtc address and multiplying it by 2 to get the address in video memory, where we're looking up directly the pixel information that's going on the screen. And so we don't want those Crtc addresses to be repeating for 8 scan lines before moving on. Now, one way we could fix this is to put a value of 0 here for the maximum character scan line. That would give us 1 scan line per character, which would mean that these Crtc addresses would be updated every scan line on the screen instead of every 8. But this doesn't work in practice because the Crtc can't count to a sufficiently high number of character rows. It can only count to 127, which would correspond to a total of 128 character rows, and with 1 scan line per character, that would only give us 128 scan lines, which, even with the small value that we can put in this vertical adjust register, wouldn't get us anywhere near the 262 that we need. So to work around this, what they did is they used 2 scan lines per character by putting a 1 in this value here, and 2 scan lines per character means that 128 character rows gives us 256 scan lines in total, plus the 6 is the 262 that we need. And in the active region, 2 scan lines per character is going to give us the 200 scan lines in total in the vertical direction, giving us our 200 resolution. So that's how it works, but of course it's at the cost of having our Crtc addresses repeated twice per character row, which is still not what we want. And so instead, what they did is they used the row address as an additional address line when accessing video memory. So you not only have the Crtc address, but this additional bit on top of that. And that means that every scan line, remember the row address is being updated 010101 all the way down the screen. By combining that row address with the Crtc address, we get a different address per scan line. And what this effectively means is that every time the scan line changes, you're changing the address within video memory by 8,192. In other words, you have two banks of 8,192 bytes, and that's how it works. So the formula is 2 times the CRTC address plus 8,192 times the row address, and that's how the CGA accesses its video memory in graphics mode to get the appropriate pixel information to display on the screen. So now that we know how this all works, we can have a look at Tandy Mode 9 and we should be able to figure out what's going on there. But the immediate problem we have is to figure out, well, why didn't they just use all the same values? After all, there's 200 scan lines there as well. And we need one more additional piece of information here. The problem is that on a CGA card, the CRTC address only goes from 0 to 4095. Basically, the CRTC can actually go higher than that, but some of the bits are ignored, and so you effectively only get values from 0 to 4095. And so we multiply those by 2, we get 8,190 as the maximum value for the CRTC address times 2, and this means that we can only address up to 8,192 bytes of video RAM in each bank. But we need a total of 32 kilobytes for Tandy Mode 9. So this just naturally implies that we need 4 banks, which of course means that we need 4 scan lines per character, so we put the value 3 here. But that means that we only need half as many character rows, and so the number of character rows in the active region is now 50 instead of 100, and of course the total number of character rows has gone down from 128 to 64, and likewise the vertical sync position gets halved as well. This is already in scan lines rather than character rows, so this value doesn't need to change. So that's how Tandy Mode 9 works. So now we're ready to think about how our linearly addressed mode might work. Now obviously if we want a linearly addressed mode, we need just a single bank of 32 kilobytes, and so that implies that we need a 0 in this value here. Then we'd be outputting row address 0 on every scan line, and every scan line the CRTC address would be advanced. And that's exactly what we need, but unfortunately it means that we need a 255 in this register here. So 255 plus 1 would be 256, plus the 6 would give us our 262, and we'd need a 200 in here because we want a vertical resolution of 200 pixels in the active region, and the sync pulse would have to be somewhere between. You might as well set that to just twice what it was in the ordinary CGA mode. And the reason we need those values is because we now only have 1 scan line per character because of this value. So we have to worry about whether or not the Tandy 1000 CRTC emulation can count this high, or is it like CGA stuck with these sorts of values? And we also have to worry about the CRTC addresses. Do they go high enough? Or do they get cut short as well, like they do on CGA? And we don't know the answer to that, but according to the notes, the EX and higher, this will just work. It can count high enough in both cases and everything's fine. Certainly anything less than the SX, it definitely doesn't work. But we don't know about the SX. Now, according to what I can find online, the SX and EX were basically meant to be functionally the same, just one is a compact version of the other. So I really don't know whether we should expect it to work there or not. But we're certainly going to give it a try, and if it doesn't work, then maybe we can use the trick that we used in the video on CGA linear addressing to trick the CRTC into counting higher by wrapping around. But we do need to worry about this CRTC address as well, and that's another issue that we might have to find a workaround for, because after all we've got one bank of 32 kilobytes now, and so the CRTC addresses have to go from 0 to 16383, and that might be too far. So let's give it a try and see what actually happens. Now I've called this program tndylin2.asm, and this can be found in my GitHub as normal. And of course it's not a very complicated program, it's just going to need to set those CRTC registers. But first of all, we want to change our TGA point drawing function to deal with a linearly addressed mode, so that if we get it working, we'll actually be able to see that it's working. So this is the same TGA point drawing function as we had before, it just doesn't deal with the banks anymore. So it's actually shorter, we've taken code out. So now the offset is just y times 160, because there's 160 bytes per scan line, plus x on 2, since there are 2 pixels per byte in this mode. And we're going to compute 2 times the offset, and right at the very end we'll divide through by 2. So this piece of code is just basically taken from the original piece of code, but I've just removed the bank part, and now we just add x to the offset and divide the whole thing through by 2, so that we get the offset instead of twice the offset, and that's it. So this now draws pixels in any eventual linear mode that we end up with. So first of all, what I'm going to do is change into TGA mode 9, which is a banked mode, and we'll actually draw some diagonal lines on the screen using our new TGA point function. And of course this is going to look wrong because it's expecting a linearly addressed mode, and we're actually drawing in a banked mode. So this is what the first part of the code does here, and then we'll wait for a key press, so that'll give us enough time to observe that this really is looking incorrect. And now we'll try and change into our linearly addressed mode. So this looks very similar to what we had previously. First of all, we have to change our CRT and CPU page register and our extended RAM page register at ports 3DF and 3DD. And I'm going to do this in the vertical blanking period. I'm going to wait for the vertical retrace before I do this. And this might just look a little bit nicer. We want to go into this linearly addressed mode as smoothly as we possibly can. And the other thing that we need to do, of course, is to change those CRTC register values to the ones that are in the table on the left for our linearly addressed mode. So first of all, we have to set the maximum character scan line to 0, the vertical total to 255, the vertically displayed value to 200, and the vertical sync position to 224. We don't need to change the vertical adjust because it's already 6 in Tandy Mode 9. But before I do any of that, I'm going to wait for the active region to start. And the reason for that is, again, just because I want this to look as smooth as possible. If I change the number of scan lines per character to 1 at a random point, then it's going to mess up the remainder of that frame. So I should do it right at the start of the next frame. And so this is why I wait for the active region before I do that. And I make sure that's the very first thing that's done, because it's the most critical one. We've got plenty of time to change the other values before the end of the frame. So that now changes us fully into our linearly addressed mode, if it works. And then we can wait for a key press so we can see the results of our effort. And finally we'll want to change back to Tandy Mode 9 again, and then finally to text mode. So going back to Tandy Mode 9 should be just the same. Again, I'll wait for vertical retrace so that this is as neat as possible. And we change our CRT CPU page register and extended RAM page register. This time we want bits 6 and 7 to be set to 1 instead of 0, because we want the values to be correct for Tandy Mode 9. In other words, we want the 4 banks back. And again, the extended addressing mode bit has to be a 0 in this case, since that's what Tandy Mode 9 uses. And now we need to change the CRTC registers back, so we again wait for the active region, and we go back to having a maximum character scanline value of 3, and we just change all the other values back to what they were for Tandy Mode 9. So now we're back in Tandy Mode 9, and we can wait for a key press again. And finally, we just restore the text mode and exit to DOS. So that's all there is to it, and basically now all we need to do is just assemble this, and then we should be able to link it and run it on genuine hardware. And once again, I'm going to use my genuine Tandy 1000SX to actually run this code, so we can see it running on genuine hardware. Well, without further ado, let's run the program and see what happens. And of course it'll start in Tandy Mode 9, and with using our new point drawing function, which expects a linearly addressed mode, and so of course everything's messed up, and that's indeed what we see. But when I press a key here, if we've got this working at all, we should see diagonal lines running down the screen. And moreover, if we've done this correctly, it should go into this mode very, very smoothly without any flicker. So I'll press a key now and we'll see if that's the case. And indeed it is. And look at that, it is actually working. Now, when I first saw this, I was mystified because the notes that I'd found in Trixter's archive by New Rising Sun seemed to suggest this had only worked from the EX onwards. And I was under the impression that the SX was released first. In fact, I'll link in the description to a German website that says that the SX was available in January 1986 and the EX in December 1986. Well, some other websites had the SX being released in 1987. If you ask Google when the SX was released, it'll just say 1984. It just gives you the date that the Tandy 1000 was released. And numerous sites have the SX and the EX released at the end of 1986. So in the end I was a bit confused and had to go and figure this out for myself. So I actually looked up some old newspapers, as they were in that day, the InfoWorld newspaper, and they had some articles about the Tandy 1000. So it seems that the Tandy 1000SX was announced either the last week of July or the first week of August in 1986, and they're actually on display in stores pretty soon after that. But then the FCC discovered that the machines were emitting too much radio frequency interference, and so they actually fined Tandy, I think $2,000 for marketing machines which they hadn't got approved. And so Tandy claims to have immediately stopped marketing them at that point, and then they resubmitted the designs, and by the 22nd of September the FCC had already approved the resubmitted designs, and the machines, according to Tandy, were being shipped. So basically the EX and the SX were actually shipped and in fact announced at the same time. And this now makes much more sense. It seems that when New Rising Sun said EX and later, he meant to imply also SX and later, and that's why this technique actually does work on the Tandy 1000SX. Of course it means, unfortunately, this is not something that I've discovered myself. We have to give the credit to New Rising Sun. In addition to that, as I said, I talked to Trixter about this, and he told me that in one of his demos, which I'll link in the description, which he believes is the first full demo on the IBM PC Junior, which has basically the same graphics as the Tandy 1000, he was able to find a 160 by 100 linearly addressed mode. So this is not new stuff. This has been done before. But at least we have it working here, and we've confirmed that it works. So that's basically going to be the end of the series. Now I do want to credit Reignite here because I included a lot of information in this video, especially about row addresses and CRTC addresses and so on, how the CGA card actually works, and all of that information came from him. He's really an expert in how the CGA card works at the hardware level. So thanks very much to Reignite for that. So to finish this off, of course, we can press a key again to go back to mode 9, and we should again see this happen very, very smoothly. And indeed, I can't see any roll or flicker there, so it seems to be working. And now back to the text mode, of course, is the BIOS's job, and here you will see some rolling. As I explained in the video, it's actually not possible to change back into this mode smoothly, so you will see a little bit of rolling as it goes back.